Hello everyone and welcome to our fourth show and tell session. This one is on asset efficiency and improvement. So some of you in the audience, you've probably been to a couple of show and tells so far, so welcome back. This is quite a short one. We're just covering 4 projects under the theme of asset efficiency and improvement. But for those of you watching who have maybe not been involved in the SIF before, or unsure how it works, I'll just do a quick run through in the next sort of 5, 6, 7 minutes of how the SIF works and why we've chosen to group these projects in this theme. So the SIF stands for the Strategic Innovation Fund. Sorry, panelists, can I just ask you to pop yourselves on mute? Thank you so much. So it stands for the Strategic Innovation Fund, and it's a collaboration between Ofgem, the regulatory body for energy, for the energy networks, and Innovate UK, the government's sort of innovation or department. So we're funded by the RIIO-2 price control, and we have a £450 million portfolio for funding over the next 5-6 years. And it happens in phases. So we start with the discovery phase, which is all about the feasibility trials, and we give people funding, give projects funding over 3 months to look into the problem, how the problem could be addressed, and you know what the potential tests and trials might look like. If they're successful in discovery, they'll move on to the alpha phase, which is a 6-month testing phase where we'll really test some of the solutions and get some valuable data out of those small-scale tests. If we believe the project is successful in alpha, they have an opportunity to apply into beta, which is our chunky one, which is 3 years worth of funding to kind of roll out, commercialize, and adopt some of those solutions into business as usual processes for the networks. The 2 key visions for the Strategic Innovation Fund is 1, to deliver net zero to the lowest cost to the consumer, and 2, to place the UK as effectively the Silicon Valley of energy innovation. So it's a really exciting place to be. I'm an innovation lead. I should have introduced myself. My name is Beth Foster. I'm one of the innovation leads here at SIF. And it's a really exciting place to be because I get oversight into all these fantastic projects that we're funding. I mean, there was 53 projects that we funded just in Discovery Round 2 alone. And today you're going to hear from 4 of them. So do keep tuned in to the show and tells, because it's yeah, the innovation that's going on here is really exciting. And just to kind of emphasize how close we are to net zero 2050, there is 9,699 days between today and our targets for net zero 2050. So all of the projects that we have here today and over the next fortnight are all playing a part in the transition and moving our networks into a more low carbon stance. So asset efficiency and improvement, we have 4 projects here. We have a project called Digital Inspector, which is led by Cadent Gas. We have another project called SF6 Whole Life Strategy, which is led by National Grid Electricity Transmission. They also have another project called SCOHL, Superconductor Overhead Lines. And finally, at the end of the session, we'll have a presentation from D-Suite, which is led by Scottish Power Energy Networks. So we have a mix of both electricity and gas here, because it's really important to emphasize that this is a whole sector problem. This is not just down to the electricity systems or the gas systems either. You know, we're working together as a unit across GB to solve these problems. And asset efficiency and improvement is really vital to unlocking net zero, because the amount of infrastructure that's required in the next sort of even 15 years, 20 years is phenomenal. And the only way we can unlock some of that new infrastructure is if we maximize what we already have. And that gives us that buffer time to build what we need to build. I mean, the Carbon Trust Committee said that we need 5 times the amount of generation that we've currently developed in the last 30 years, we need to multiply that by 5 by 2035 to meet some of our net zero targets and forecasted demands. So the amount of assets and infrastructure that's required, as well as maximizing what we currently have, is really, really like an important part of what we do here. So without further ado, I'm going to hand over to the projects. But before I do that, just a little bit of housekeeping, please. If you have any questions, please pop them in the Q&A box. If you pop them in the chat, unfortunately, we won't be able to get to them. So please use the Q&A for the project presentations. If we run out of time, I will ask the projects to directly answer the questions in the Q&A, just so we can keep to a schedule, as we've got quite a bit to get through today. So let's go to the agenda, please, Chloe. Brilliant. So we have a nice list of projects here. So we have Digital Inspector. They're looking at some of the ways we can monitor some of the welding on the gas pipelines. And then we have the next three are looking at the sort of way we monitor and optimize some of our electricity system assets as well. So I'm really excited to see what the projects have today. So I'm going to hand over to Digital Inspector first to kick off our first show and tell. Over to you guys.
Awesome. Okay. Welcome all to the presentation of our project, which is Digital Inspector. Next slide, please. I'm Lewis Watts, Head of Engineering at United Living, and I will be providing the introduction and general overview of the project. One of our partners, Triton Electronics, will be providing a bit more sort of deeper insight into the specific work packages that we undertook during this discovery phase. Next slide, please. So, as our energy future changes around us, so must do the future of work. The way we work on site and how we collaborate as customers and contractors needs to shift to keep pace with technology, society, and competition. So, how did we deliver this? Well, it always starts with a problem. Next slide, please. Welding is a critical path activity. Critical path activities are the tasks that determine the minimum time necessary to complete a project. Delays on the critical path affect the entire scheduling of a project, which almost always results in an increased cost to construct, either for the customer or the contractor, but ultimately feeding into the cost of our energy at home and at work. Collecting, collating, interpreting, and improving welding data is currently a really and very manual process, which is prone to error due to its complexity. This makes welding a time-consuming and resource-hungry task. So this project seeks to reduce the complexity, the time, and number of resources required by leveraging novel digital technologies to create a site ecosystem called Digital Inspector. Next slide, please. So, on to our findings. Next slide, please. Digital Inspector will be a complete ecosystem for monitoring and managing welding across multiple different locations simultaneously by connecting back office functions such as procedure approval and welder approval databases to site tasks with real-time weld data acquisition. The project is designed to be scalable and serve as an innovation platform for further site digitization, such as non-destructive testing, digital data, and connect to other software as a system services, such as building information management, or BIM software, as it's commonly known. The successful delivery of the overall project concept will improve energy system resilience and robustness through improved quality. So things such as early identification of fabrication issues and non-conformances. But it will also improve construction transparency, such as the requirements for rework and lower cost through reduced downtime. Next slide, please. The contractor, United Living Infrastructure Services, which is who I represent, and our customer, Cadent, have identified the needs of the system in the orange box on the left. As we've progressed through the discovery phase, we have refined these needs into macro actions on the right, but the project refers back to to remain focused. The first 4 points refer to reductions in construction costs, production costs, project delays, and embedded carbon, with the next 4 points referring to transparency, such as the visibility of construction and real-time monitoring, and really the future-proofing of the investment through scalability and quality. So we've refined these on the right, and they've transformed into tangible outputs and, I suppose, guideposts. So, for example, by eliminating double and triple handling of data, reducing the amount of traveling needed by staff members, multiple user logins for both the customer and the contractor, an open-ended design ready to receive new modules and upgrades. Next slide, please. So the refinement of the user needs has led to several opportunities across 3 major pillars, and we've identified these as software, hardware, and accessibility. For example, the project needs software that must be sympathetic to site, as well as office operations. It's got to be scalable and agile and usable across multiple platforms, such as phones and tablets, but also readily linkable to other software via APIs. So this is a computer software that translates between one and the other. And currently, nothing of this scope exists on the market that could be identified by any of the parties involved. We also need new hardware so that the project does not lock the technology to a brand, removing obsolescence and further sunk costs. Yet it's got to be reliable and ready for upgrades later. And finally, accessibility. So transparency builds trust, and thus building a system that allows the customer to see and measure the same data as the contractor enhances relationships. Whilst the future workforce is considered to be tech savvy, the project partners recognize the current workforce is often technology shy. Therefore, users' interaction with the system must be simple and logical, requiring really minimal training. In the following slides, our project partners will deep dive into our work packages and provide proofs of concepts for some of the software and hardware options available to us. So, without further ado, I'd like to introduce James from Triton Electronics.
Thanks, Lewis. Hello, I'm James from Triton Electronics, and I'm going to take you through the outputs of the discovery phase on behalf of all the project partners. Next slide, please. Digital Inspector is going to modernise and digitise the way that welding projects are planned and welding on site is performed. There's a need for this innovation to bring together existing software and processes which work well independently but are fractured and inefficient into one system. This will streamline processes, allowing for time and cost savings, but also provide verification of data, prevention of errors, and lead to better use of data in the future. By providing an ecosystem for the digitization of this data from start to finish, we are also starting the development of a platform which can be built and expanded upon in the future. There's scope for other projects, and as technology develops and our understanding of data improves, the potential for AI-driven planning and optimization tools, AI-driven defect analysis, and more. TWI already provide market-leading welding qualification and planning software packages, Welding Coordinator and Welding Qualifier. Triton have been developing monitoring hardware for over 25 years and have recently started providing some cloud-based data capture tools. In collaboration with United Living, Cadent, and National Gas, we've designed a platform which will seamlessly integrate TWI's software with a new dashboard service developed by Triton. The dashboard will provide project tracking, intelligence, and collaboration tools. We're developing an inspection app, which will integrate seamlessly with the project and provide real-time data verification on site. The data will then be indexed and retained for long-term storage and analysis. We believe this platform will coherently address the user needs outlined. Next slide, please. This slide shows an example of how things are currently. As you can see on the left, important documents are filled in by hand. These will most likely be copied into an electronic format at a later stage, which increases the risk of error due to double entry and the human factor. On the right, you can see printouts from a monitoring device. These are glued onto paper and put in a file. The problems we're highlighting here are multiple data entry, large room for mistakes and errors, and no automatic data validation or verification. Next slide, please. A key output of the project, which has been led by TWI, is the conceptualization of what is a digital weld. There is currently no standard in place, domestic or international, which aims to define the variables and data which make up a weld in the digital space. This output will help standardize the definition of a weld, while also facilitating the communication between project components. We believe by completing this work, we'll provide an important output as a net gain, which can be shared internationally. TWI have started the process of defining a digital weld. The standard will have 3 levels: core variables, other process-specific variables, and procedure-specific variables. This standard will be worked on and developed as the project continues on, hopefully into alpha. Once data starts transferring between project partners, we'll gain a unique insight into what we believe need to be included, and also any areas of the digital inspector ecosystem that can be standardized. We're keen for Digital Inspector to provide a platform which is configurable, modular, and can be expanded upon easily in the future, with other third-party tools being able to integrate, and with users of the platform being able to transfer data in and out of the ecosystem with ease. Standardization will maximize the benefits Digital Inspector can provide to pipeline welding and other industries. Next slide, please. As part of the Digital Inspector project, we want to provide a new, innovative, low-cost monitor. The monitor will work with any welding plant, be completely unobtrusive and interchangeable, so it can be used on a rented plant, and if one breaks down, quickly swap with another to minimize delay in welding. This new monitor is key to addressing the identified user needs while also being a good opportunity in itself. We're developing an inspection app which will act as the control interface for the new monitor, but also as a digital record keeping tool for inspectors when they're on site. They'll be able to view all relevant data about the weld they are monitoring, such as the WPS and any drawings. And real-time verification will mean that costly errors, which can go unnoticed for weeks, are a thing of the past, because inspectors can be sure that the materials, consumables, and welders are valid as per the specification for that weld. Fab reports are completed at the same time as the weld, instead of days or weeks after the fact. This report then updates the bar chart, which is the live document maintained by inspectors as various welds are completed. This will provide an up-to-date tracking facility, which both main contractors and subcontractors are able to view and be sure that the jobs are proceeding as expected. If issues do arise, all parties are kept up to date, increasing visibility and trust. For Digital Inspector to function, it's very important that the monitors and inspection app have an internet connection. Pipeline welding sites tend to be in the limited areas of the country where there's no 5G or 4G connectivity. This is a problem which we needed to address in Discovery because it's critical to the functionality of the platform. We found a novel solution. The monitors will have a built-in ISM mesh network, which will enable connectivity across the entire site, so the monitors themselves can distribute a satellite internet connection. Next slide, please. The dashboard is the central hub of Digital Inspector when welding is taking place. We worked extensively with United Living engineers to gather requirements and gain an understanding of what the processes are currently and how they can be digitized effectively. The goal of Digital Inspector is to provide these tools not only to the organizations carrying out the work, which in this project is United Living, but also their customers who have a desire to also maintain an overview of what's happening at their sites at any time. And that would be Cadent and National Gas in this project. As part of the dashboard, we're building an API in collaboration with TWI. This will mean that the data can be seamlessly transferred from their project planning software at the point when a site is nearing going live. From a technical perspective, we spent a lot of time considering security and data protection processes to ensure that Digital Inspector is a safe suite of tools for use in sensitive environments. Once the data has been transferred to the dashboard and a pipeline site is live, the dashboard will provide a central location for all data being captured by multiple inspectors and monitors at that location. Collaborative tools will make responding to issues and events far easier, with quick responses meaning cost savings due to fewer delays. The monitoring app and the monitors will highlight any issues as they arise, whether it's due to welding parameters being out of range or the specification or incorrect material use for a particular joint. We will also verify welder qualifications with TWI's welding qualifier software. Digital Inspector will mean that if conditions for a weld are wrong, it will be flagged before going ahead. Currently, mistakes might not be flagged until the project's long continued on, meaning costly delays as the mistake is cut out and rectified. As part of Discovery, we went through a requirements gathering process with all the parties, resulting in our identification of user needs, reports of our findings, and some software concepts and mock-ups, which you can see on these slides. Next slide, please. With a desire for Digital Inspector to be a platform for future innovation and growth, we believe that under the umbrella of site intelligence systems, we can design the platform to be easily fed more data streams and expanded upon in the future. We believe this could take the platform in a number of directions and understand that with the rapid developments taking place, in AI tools in particular, it's important for us to design the platform in such a way that we're ready to exploit this. We wanted a method to display in a high level and easy to understand way all of the data we were capturing from the monitors and inspectors. As an example application of the use of the data, we believe having a visual history of every day that's taken place on site will be useful for quickly scrolling through the major events that have taken place. United Living, the contractor, or Cadent National Gas, the customer, can drop in and see which inspectors are on site and where they are, but also which monitors are switched on and capturing data. This data will also be stored, so if the customer wished, they could fast forward through the last week on site, seeing a quick summary day by day of which welds were completed, where they were on the satellite map, by who, and who was inspecting. This data could then be piped off into a different system to be used for future optimizations, predictive models, or something else. Digital Inspector creates a unified platform for storing data so that in the future, we'll have a reservoir of data that can be interrogated for future planning and analysis. We believe that Digital Inspector can be itself a platform for innovation in the future of large construction projects and the drive to net zero. That's all for me. I'm going to hand back to Lewis.
Next slide, please. Thanks, James. Okay, so to conclude the presentation and summarize the project benefits, let's take a closer look at what each stakeholder can expect to receive, starting with the customers, such as Cadent. So for Cadent and National Gas and gas customers initially, but though this will scale into other sectors, the overall cost of constructing assets is reduced and streamlined by live tracking of costs, reduction of site personnel, and a lower likelihood of project delays due to welding. Critically, for this particular funding period, or the RIIO-2 funding, we expect that it will go further than originally predicted because of the net gains from this project, the streamlining and less rework, as we've discussed previously. And then there's further opportunities for site digitization, and these can be realized by using this project as an innovation platform for other digital bolt-ons. And we have a few ideas for that for other projects down the road, but its open-ended design is specifically so that you can attach other digital technology to it without necessarily adhering to the full ecosystem. The contractor, so there's a benefits for us as the contractor. Well, we'd be the front of industry innovation and high quality fabrication. We'll have improved productivity and reduced construction risk, which is probably the key one for us. And ultimately, that means we offer a significantly more competitive service. For our partners, TWI and Triton Electronics, they get to have new hardware and software, so within their existing markets, but that opens up new markets for them and their shareholders. And then finally, we have big data statistical control. So big data is one of those terms that's quite popular and I quite hate, but it is good in the correct format. And in here, the statistical control that we can draw from big data, and with further prediction models around AI, say like neural networks and foundation networks in AI, there's huge potential for being able to do all sorts of very practical things with digital data, as opposed to just data giving you a pie chart or a graph. And then the consumers, well, for the consumers overall, there's the increased productivity and traceability in the gas sector. There's the lower cost of a regulated asset, so this cheaper to build. So thereby providing an ultimate financial benefit to us as the end user or customer. The project improves the robustness and clarity of future energy systems, and future upgrades to the network, cost less to implement. So the idea of this project is that we can bolt on into the future, looking at that 10, 20 years ahead when we are upgrading the network again, or we're finding that we need to finalize a few bits and pieces. The system isn't locked, and we're able to, push it forward and add stuff later dates. And that's it. And that's it from us. So next slide, please. Thank you. And sort of questions. Anyway.
Brilliant. Thank you so much, Lewis, and the rest of the team for a fantastic presentation. Really thorough. So we haven't got any Q&As in the box right now. So I'm going to kick off just because I have a gas operations background. So it's really, really interesting for me. So in terms of the technology itself, what actually is the technology? How does it monitor the welding points in the pipelines?
I'll hand over to James for that one because he's all over this. Understands more than I do.
So what our existing monitors do at the moment is they're monitoring various sort of factors which are taking place as welds are performed going around the pipelines. I guess what digital inspectors now going to do though is bring that. At the moment, inspectors will have these devices and they'll turn up and they'll leave and they'll fill in their reports and they'll do everything sort of off-site or after the fact. These devices literally print out, reels of paper with the parameters that they've monitored as these welders are performing these welds, which can take 4 hours. And then really it's up to the inspectors then and the teams in the office to, go back over and verify that everything was okay. And that also that everything would, all of the materials and everything that were going into that weld, so 2 bits of pipe coming together and that kind of thing, were all valid. So really what Digital Inspector is bringing is all of that pre-planning material is then integrated within a system. The inspectors on site are no longer sort of offline, making notes on a piece of paper and, using printouts and that kind of thing. It's all recorded digitally and then it's verified because the integration with TWI's planning software means that we know that when these weld joints were planned months ago and they were tested as well. So when you build a specification, you actually perform tests to make sure that the materials can go together and that kind of thing. All of that data is immediately accessible so that when things go together, welds are performed, we can be performing tests on the specifications that were specified months ago and just checking that everything is legit, basically. What has happened and what can happen is sometimes materials on site are wrong or sometimes there's unexpected pipe, that kind of thing. And, mistakes do happen, can happen. And those mistakes in the context of a pipeline site, if they're not identified immediately, can, run into hundreds of thousands to rectify. So really bringing everything together in a manner that it can all be verified in real time with the collaborative tools we've sort of been explaining and that kind of thing. That's what Digital Inspector's about, and that's what we're trying to do. Brilliant.
Thanks, James. We have 2 questions in the chat. The first one I think we've sort of covered, so I'm going to jump into the next one to save time. Could this solution help improve the insurance process in terms of risks and claims by providing better information on the network assets?
So I'm going to hand that one back to Lewis because Lewis knows more about that coming from that sector, but I think.
Yes, so we've taken the approach of this in terms of risk mitigation, but also risk allocation. So quite sort of the same sort of thing. You're looking at risk, but they are different streams. And yes, because it's data validation in the moment and real time, and then correction happens in real time too. It enables us as contractors. So as I'm physically building the pipeline, I'm able to correct an error immediately in the day. Now, it sounds like an obvious thing, but it doesn't happen at the moment because a lot of your records are delayed, or you may pick up something down the road. You can't have an expert that the insurance companies would like to have at every single point for every single service, for every single event that takes place. Instead, what traditionally happens in pretty much every company is that you'll have a base that supports front site. So site have their own experts, but not everybody's an expert. And then you have the back office. And this will reduce risk across both front office and back office systems. And it was crucial that we had that piece in so that we could have a lowering of insurance and a lowering of risk overall, but then be more fiercely competitive, I suppose you could say, because the actual costs of construction are easier to identify. And so thus the risk of something going wrong in the cost of construction are also able to be quantified much easier. So yeah, I hope that answered the question.
Thank you. Thanks, Lewis. Thanks, James. I'm afraid we will have to move on now. Thank you for your presentation and your time. There is one question left in the Q&A. Would you mind just typing an answer into that while we move on to the next presentation?
Absolutely.
Brilliant. I'd like to invite Jack and Tony from SF6 Whole Life Strategy, led by National Grid Electricity Transmission, to present their next show and tell. Over to you guys.
Hi, Beth.
Hi.
Thanks for the introduction. I'm actually standing in for Jack today. My name is Ben Brewer and I'm a principal consultant at DNV. And I'm actually signed in with Tony's link, so you'll just have to ignore the name on my video for now. But thank you. So I'm here today to present our work so far on the SF6 Whole Life Strategy at this discovery phase show and tell. Next slide, please. So outline agenda for the day for this 15-minute presentation. First of all, we'll look at SF6 use in the power sector across GB. We'll run through a quick project overview as to what we've been doing so far. And then we'll look ahead and at the next steps in terms of taking this forward to alpha phase. And then we'll invite questions through a general Q&A for the last part of the session. Next slide, please. So SF6, what is SF6? It is sulphur hexafluoride. It's one of the most potent greenhouse gases that we know. Its high atmospheric stability and ability to trap infrared radiation means that it's far more potent in terms of warming the Earth's atmosphere than carbon dioxide over longer periods of time. Indeed, across transmission networks and distribution networks, we estimate that after technical losses, SF6 leakage from assets is one of the highest contributory factors to greenhouse gas emissions across networks. And to put the potency into perspective, you can see on the bottom left with the small blue square, this is 1 kilogram of SF6 and it's equivalent to 24,300 kilograms of CO2. So it's a very high potency gas. Annual emissions of SF6 between 2012 and 2022 rose by 47% as networks installed more GIS, gas insulated switchgear. Annual global SF6 emissions were equivalent to yearly CO2 emissions from 44 million passenger cars. And to put that into perspective, in the UK, there are 33 million cars on the road today. This is also the equivalent of 103 million tons of coal, and National Grid has the ambition to reduce SF6 emissions by 50% by 2030, working towards complete removal of SF6 gas from electrical assets by 2050. Next slide, please. So just a brief overview of the project. In the italics is our pitch statement, if you like. So we are developing an economic, efficient and holistic replacement strategy for SF6 free, to be SF6 free, that will support GB's ambition to facilitate a net zero and resilient energy system. Partners on this project is main lead is National Grid, Electricity Transmission, supported with project partners who are DNV, University of Manchester and SSEN. Key activities in the discovery phase are to, and potential future stages are to develop and assess options that are available for replacing SF6 in existing assets and going forward, and to develop a high-level plan of the testing that's required to validate the replacement strategies that are recommended through this project, and to undertake a techno-economic analysis to underpin this strategy in terms of identifying when and where necessary interventions should be taking place in networks when replacing SF6 gas. And this is targeting the Innovation Challenge 3, which is improving energy system resilience and robustness. Next slide, please. So what have we been doing today? We've held a combination of in-person workshops at University of Manchester, where the project partners have come together. And we've held a number of online meetings as well, as weekly recurring. And in these meetings, we've been refining the work packages and working through some of the more technical detail, reviewing the various work streams on the project as well, and just keeping track of project program and sort of reflecting on deliverables as well. We've been gathering and processing SF6 leakage rate data from networks, and we've been developing an understanding of which assets require intervention and quantifying those leakage rates as well. In terms of our methodology, we've been defining that at this stage and also carrying out some techno-economic analysis. So for instance, we've selected two substations which are national grid sites with quite different profiles in terms of the age of the assets there and the SF6 leakage rate from those assets as well. And we've been preparing a cost benefit, a techno-economic analysis, which captures parameters such as carbon credits and cost of carbon from HM Treasury Green Book, for instance. And we've been calculating the net present value based on the application of different intervention options. So whether it's retrofill, leak repair, refurbishment, or early replacement of those assets. And we put together a comparison looking at those different interventions across the forthcoming years as well. And then finally, we've been scoping out the next phase of the project as well and preparing an alpha phase submission application. Next slide, please. Okay, so I'd just like to hand over to Tony. Thank you.
So carry on from Ben then. So first of all, just to cover what are the main sort of SF6 replacement interventions. Really, you can broadly divide it into three groups. So we start with the first one on the left-hand side of the screen, which is new build. So effectively, this is to decommission the entire SF6 substations and replace it with a new substation equipment using a new gas that's optimized for those new equipment. So the first one was actually installed in the UK back in 2017. So already about 5 years of service experience already. So we found that the leak rate was marginally higher than the equivalent SF6 leak rate. So this was in Sellenge, UK. But the problem with this approach is cost and time consuming. So to put into perspective, a complete new build could cost in excess of 100 million. And there are over 100 gas insulated substations using SF6 in National Grid's inventory. So it's quite costly to do a complete replacement of all those substations. And it's also a time issue as well. Each of this GIS can take years to complete. So the one in the middle is some of the research that was initiated at Manchester, which is look at can we develop a retrofill solutions. Like the name suggests, is to take the SF6 out of existing legacy equipment and to replace it with a more environmentally friendly alternative that obviously with a significantly lower environmental impact. So it's found there was a solution, an optimized solution that can give up to 99% reduction in the equivalent carbon footprint, and basically without modifying the rated pressure or having to open the equipment. So literally gas out, new gas in. We'll have to change the density meter and also make some small modification to the desiccant, which don't require the opening of the bus bars, which then becomes quite costly. So the first retrofill operation in the world was again accomplished in the UK in Richborough, Kent by National Grid, which was energized in December 2021. So still sort of early days for these two solutions. The last one is leak repair. So there are certain, so the key thing to remember with retrofill is the costing is mainly just the gas and the labor. So the cost is then it's only a few million rather than excess of tens of millions or even over 100 million. But retrofill doesn't work on all of the legacy equipment because there's compatibility issues. At the end of the day, we're putting a new gas into equipment that's optimized for SF6. So certain equipment will end up being too leaky to trial the retrofit solutions. So what National Grid sort of done in parallel is working with other partners to develop leak repair solutions. So so initial pilot trials was already being done in the DSITE Center for Innovations. So this is using innovative sort of molten metal manipulation technologies developed by Raw Water. So you can see from the photo, so the ball valve, so what effectively you see there is solder irons on top of the ball valve, and that basically seals majority of the gas leak from SF6. So that has been successfully trialed in De Norwich and Sizewell substations. So those are the sort of three main intervention approach. Next slide, please. So then we kind of look into the leakage rate insight. So how do we decide which substation to use which approach? So the key thing to point out, the leakage rate here is a top up in kilograms converted into leakage rate because National Grid hasn't got leakage monitoring for every single substations over since 1960s. So these are top up in SF6 in kilograms converted based on the total inventory data. What we can broadly see is the older assets are more leaky and the modern assets are less leaky. But with time, the leakage rate will naturally increase for these equipment. And you can see that majority of the assets actually installed since 2010, so in the sort of last 10 to 15 years. So really the 4.6% of asset that's kind of reaching the end, fast approaching the end of life. The reality is you can probably look for one-off permanent leak repair solutions to extend the life a few more years until they're ready for full replacement. The one, if I go straight to the 66%, which are in the early stage of their asset lifetimes, they're really not suitable for a complete replacement because they can still function for another 40 years or 50 years before final replacement. So it would be very costly and ineffective to replace them now. So they're potentially more suitable for retrofit. The ones in the middle, a decision would have to be made on a case-by-case basis. Some might be more suitable for the leak repair, and some might be for retrofit, depending on the leakage profiles. So that's a broad, kind of quick insight into the leakage rate on all of the National Grid's SF6 assets here. Next slide, please. So just to touch on to the sort of the key insights and benefits of this project. So the project is really about to enable more efficient and timely interventions on SF6 equipment to identify that optimum approach based on the difference of asset types. So as mentioned previously, a complete rebuild is very, very expensive and time consuming. And to do that for 100 substations before 2050 would be impossible for National Grid. So really we have to identify different approaches, which is something that we've done in the discovery phase. Then is the techno-economical analysis to demonstrate that benefit through the reduction in carbon credit costs, but it's also the societal cost of a more low carbon approach going forward, associated with the retrofill, leak repair, but also early replacement ahead of the end of the lifetimes. So we look at the use of automations in the gathering and analysis of SF6 data, because as I mentioned, at the moment, the recorded data is top up of SF6 and converting that into a leakage rate, which is not indicative of an actual leakage profile of the asset. So having that would allow us to make a better assessment to determine the optical interventions. As mentioned, there are certain solutions available already, and they tend to be in mixtures, so 2 or 3 gases are mixed together as a replacement of SF6. So for those ones, there's a problem when it comes to the site handlings as more and more alternative being used. So the mixture ratio could be different. That could lead to cross-contaminations or maloperations, where procedures or technology must be developed to safeguard against that. And as we phase out SF6, removing thousands of tons of SF6 from the network, then we really ought to find alternative ways to dispose SF6. At the moment, just literally throw the SF6 bottles into a furnace and burn it at 1,200 degrees, which is quite a highly carbon intensive approach to store it. So the next phase of the demonstration work was to look at the laboratory scale testing to demonstrate the low carbon approaches possible. And finally, the last one, system access. If we have areas like London with a very high density of GIS due to space constraints, then we can't just take all the substations offline. So we'll have to look at evaluating the system access for different substations to ensure that we can carry out the SF6 interventions in a timely manner. And I'll pass it back to Ben for the last few slides. Yeah.
Thanks, Tony. So we're approaching the final stages of discovery phase. We're preparing the report at the moment. And then, as I mentioned earlier, we're also preparing an application for the alpha phase as well, where we really look to take this to the next level of detail, exploring opportunities and barriers to the various SF6 interventions that we've defined in the discovery phase. We'll take a machine learning approach to SF6 leakage assessment and look at the practicalities of handling site gases, gases on site in terms of removal from assets, and laboratory testing of disposal methods as well, in terms of destroying the SF6 or recycling, and understanding system access implications as Tony explained. And then if this was to progress to the beta stage, then this would include a large scale demonstration of interventions, of the effectiveness of those interventions in situ on sites, and would sort of culminate in developing a holistic rollout strategy across other eligible sites as well. And then from that stage, we would anticipate that it would be a business as usual process to implement that strategy across networks. And all through this process, we'll be disseminating the findings as well as we go along. Next slide, please. So in terms of next steps, just finalizing the discovery phase report and techno-economic analysis, on preparing a submission for the alpha phase proposal as well, and building on the learnings of the discovery phase. Sean Coleman is project sponsor from National Grid Electricity Transmission, so feel free to reach out on further details on this project, and you can see the overall timeline there of the alpha phase as well. And I think that's all I have, so I'd like to invite questions from attendees.
Thank you so much both for a very interesting presentation. Again, we're a little bit slow on the ground with questions, so I would like to invite the participants to pop their questions in the chat box. But to start with, so I'm quite curious, what sort of technologies are you using to actually detect the SF6 in the assets?
So at the moment, there's different technology being used. The most accurate one is to have pre-installed density sensors, so they can record the exact volume inside, and also pressure sensors to monitor the leak. But those ones, the problem is they record the data for a 6 months period, and then it's get overridden because of data storage issues, like with many sectors at the moment. So the issue with that is it doesn't give you, so you saw from the leakage profile, you can only see a trend over sort of a 50-year period. So with 6 months, it's very difficult to make that assessment. So that's where we need a bit of automation and maybe a bit of machine learning as well in there to look at the leakage profile and forecasting of leakage going forward.
Yeah, I was going to say there seems to be a really good opportunity here for some AI technologies to come in to help with those analytics, and also perhaps maybe some innovation in data collection processes and things like that. So for the innovators on the call, make a note of that. There are opportunities here. Oh, we have some questions coming in. Is there much activity in SF6 recycling within transmission and distribution networks? And is this considered within your project?
So currently, I think one of the main suppliers for this, for National Grid, is Celtic Recycling Ltd, based in Newport. So they do take in a lot of the used SF6, There's some challenges because some of the toxic byproducts cannot be easily filtered, like S2F10 and CO. So potentially, if you as you recycling, you're getting a buildup of very highly lethal toxic byproducts. So these are issues that we have to look into. In terms of consideration in this project, what we're considering is more method of sort of low carbon approach to incinerate the gases in the future, as we kind of move into a phase where we basically no longer need to use SF6 going forward. Yeah.
Thank you, Tony. So I have a question from Rob Walden here. Do you have any telemetry that tells you that there is a leak or that a leak is developing? And does this data get sent OTA to a monitoring center?
I'm not sure it's that sophisticated. So I've been to substations where literally is hand recorded on a piece of whiteboard of how many kilograms of SF6 top up. Generally, all these substations that will have the equipment will have a low pressure monitoring alarms. So that will obviously trigger, and then the operator then need to top up the SF6. And by regulatory requirements, because this is a very potent greenhouse gas, you have to record how much you top up. So that's generally the moment here. So I mentioned some have a monitoring, continuous monitoring, but it kind of is for a 6 months period before the data get overridden. So it helps for you to make local assessment on where the leak is and how the leak is developing, but it doesn't allow you to have that historic data and allow you to really forecast. So when you look at the forecast scenarios, it's very much like almost a linear increase if no interventions, and if with interventions, it's a percentage decrease. It's not that automated, I would say. Yeah.
And just a second part to Rob's question, does the 6 month data collection struggle with seasonal variance at all?
That I'm not quite sure. So when we went to the leakage data, we didn't see a real trend between winter and summer, whether there was more top up or less top up, if that was the question. Yeah, if I understood the question correctly.
Okay. And one last question from AO. Is the plan to produce a decision-making framework for choosing intervention strategies? And if yes, will it be transferable to the distribution network level?
So the first one is absolutely the plan here, because there's not enough, I think, investment that can be made to replace everything in one go with a new build. So we'll have to look at different intervention strategies. And the second question is yes as well. The first is focusing on transmission because it's where the greatest win is, and then moving to distribution level going forward.
Brilliant. Well, that's all we have time for Q&As on this session. We're going to take a very short break. Let's do 6 minute break and have everyone back by just after 3 o'clock, and we'll kick off at 2 minutes past 3. Thank you, SF6 team, for your presentation and your time today. And everyone else, be back to learn about superconductor overhead lines with National Grid again. Cheers. So see you all at 3 o'clock. Just give it a minute or so to welcome people back, and then we will kick off on the next show and tell. So welcome back, everyone. We have 2 more projects this afternoon for you. We have superconductor overhead lines led by National Grid Electricity Transmission. And we have D-Suite, which is led by Scottish Power Energy Networks. So 30 more seconds, and then I will hand over to Alison. Bear with me 1 second. Okay. So Alison is going to take you through the potential of high temperature superconductor technology on overhead power lines in the UK. Over to you.
Yeah, thanks, Beth. Yes, I'm Alison Strachan. I'm a consultant at Fraser Nash, who's one of the team working on this project. And I'm going to take you through the presentation today, and then we have other members of our team from the different partners available to answer some of your questions at the end. So if we could have the next slide, please. Okay, so yeah, our partners on this are National Grid, who is the project lead, National Grid Electricity Transmission. And we have VIA, who are developers of the technology that we are going to be talking about in this project. We have the University of Strathclyde and the University of Manchester, who have been doing some of the analysis work for us, and Fraser Nash, who I'm part of, who've been doing some of the road mapping and the techno-economic analysis. If you could go to the next slide, please. So this afternoon, I'm going to give you an overview of our project, tell you what a SCOHL system is and what possible use cases there could be for it, what the key findings we have from our discovery phase, so split into 3 categories: technical challenges and opportunities, a bit about the costs and benefits, and then some engagement with other interested stakeholders that we undertook in the part of the project. We'll then talk about the roadmap, so the roadmap to get this technology to business as usual, and what we have planned for the alpha phase, and then we'll have some questions. So yeah, next slide, please. Okay, so project overview. So as Beth said in her introduction, obviously there's a huge ambition if we're going to achieve net zero, and that's going to mean a significant increase in electricity demand for various different industrial sectors and domestic sectors too. The usual way, if you're going to increase the capacity of a circuit, one of the usual ways is to either add an extra circuit, but if you already have a lot of circuit capacity, you can increase the voltage. So if you have a 275 kilovolt circuit, you can increase the power capability on that circuit by raising it up to a higher voltage. Unfortunately, that can be a bit of a problematic thing to do, because as you're going to higher voltages, you have potentially long consenting times for these projects and long lead times, because obviously as you're going up to higher voltage, you have a higher visual impact. The towers are bigger. There's bigger width of corridor required for the technology, and there's also the construction can be more complex and require a bit more specialist equipment. So therefore we propose a solution to that would be SCOHL, so superconducting overhead line technology. These could be used to operate existing line routes to achieve up to 5 times higher power capacity, and also reduce or remove the need to use conventional 400 kV, so reducing the cost and footprint of the infrastructure like I just described there. Next slide, please. So what is a SCOHL system? Okay, so superconductors, the SC, are materials that have almost no electrical resistance at low temperatures. And what we're looking at in this project is high temperature superconductors, which are still pretty cold, but they operate at the temperature of liquid nitrogen, which is around minus 196 degrees Celsius. And liquid nitrogen is a common industrial coolant. So earlier superconductors were, cooled by other gases which were very close to absolute zero and very difficult to bring out into the field. Whereas with liquid nitrogen, it's a very common industrial coolant, so you can use it in more applications. So our project partners VIA have developed a novel open loop cooling system that allows high temperature superconductors to be deployed as overhead line. And the reason that this works is that cooling with liquid nitrogen in a closed loop system has significant weight issues associated with it. And that kind of restricted high temperature superconductors to cables, so underground cables only. But this novel technology, which there's a paper there which describes the science, which is really, really interesting if you want to go and read that, has this open loop cooling system which removes or reduces those issues. And the system that they've developed comprises HTS tape, which is the conductor, in an insulated jacket, which provides the cooling. And then there are pole top units along the line to manage the temperatures and pressures of the liquid nitrogen. And that picture there is one of the pole top units that they've deployed and they are testing at the moment. What it is, it's a transformer can size, usually used. Those sort of transformers are usually used at distribution in the States. So it's relatively small. It fits, as you can see, on a pole, a distribution pole there. You could do the next slide, please. So what are the possible use cases for this technology? Okay, so we came up with a number of different scenarios, and we reduced them to, in the discovery phase, to the three most useful cases, I suppose, are the most prominent cases. So the first case is, as we've probably already discussed, upgrading 275 kilovolt lines to 400 kV. So because, as I said, the power density can be increased at 275 using superconducting lines, you're basically increasing the power capacity without uprating the voltage and without making the infrastructure a lot bigger. So that's a very big advantage that we'll talk about a bit later on. The second use case that we came up with, there's a potential to use future overhead line to underground cable superconducting network. So some of you may be aware that we've also been working on another project called SCADent, which deals with underground superconducting cables. So potentially what we see here is a linkage between the overhead line and the underground cable, so that, for example, it could be used in areas of outstanding natural beauty, where we could bring a superconducting overhead line up to the boundary, underground the cable using HTS through the sensitive area, and then go back up to an overhead line after that. And then the third case is again very relevant to the net zero ambitions. It's a rapid deployment of new network infrastructure. So as we talked about earlier, for operating lines, you get much longer consenting periods because of the various regulatory issues around those. If you are building new lines with 275 kV as opposed to 400 kV, you can potentially get those connections made quicker and therefore bring online more renewable generation at an earlier stage, or supply additional demand at an earlier stage than you would be able to with a conventional solution. Next slide, please. Okay, so from our discovery phase, the key findings, the first one I'm going to talk about is technical opportunity. So there is a huge opportunity for this technology. As we've said, significant amount of network needs capacity upgrade to deal with the increasing demand and the renewable generation that's coming on stream. And that there's a number of projects and funding initiatives are going on. For example, ASTI at the moment that recognise that, and this would be another one to add into the sort of various suite of options that are being talked about. There is over 4,500 kilometres of overhead line in England and Wales, which makes up 95% of transmission circuits. So this has a big potential to be used on the network. And that system also comprises around 22,000 transmission towers and around 340 substations. So you can see it's a pretty big job to upgrade the network. So if we can come up with good solutions to do that, that's also good. Now, reconductoring circuit, so basically putting in a higher capacity line, is a fairly common practice. So it's not an unknown thing that you could replace one conventional conductor with, for example, a superconducting line. And SCOHL, like we say, is another technology that could be used to add to that sort of the suite of options that are available to National Grid for these upgrades. And one of the things that we found in our research for the discovery phase was that many of the towers that are on the network have existing CAD structural models that we could use or modify so that we could understand the structural issues posed by the different technology that is SCOHL. So effectively, we're not starting from a blank sheet of paper there. We've already got some models that we could reuse in order to test out some of the challenges that we face with the SCOHL technology. Next slide, please. Okay, so technical challenges and issues. There are several different designs of transmission tower on the grid. There's a couple of examples just there on the slide. And each tower is going to have specific structural issues related to its site and also its application. So some towers are suspension, some towers are in tension, and some are obviously terminations where when you get to the substation. So those are there's a lot of different structural issues that we would have to examine if we were going to roll out this technology. And if we wanted to retrofit to existing towers, we need to understand exactly the structural issues that are related to that. Now, 275 kV towers, which is what we're looking at for this project, are generally about 300 meters apart. And the current development of SCOHL is focused on lower voltage systems for about a 75 meter span. And the first commercial project there is expected in early 2027. Now, being involved in this project does allow potentially an accelerated development of higher voltage SCOHL systems. But obviously we have to take into account that if you are developing a conductor for a longer span, it needs to be thicker and heavier just to maintain the structural integrity. So that's the kind of issue that we would need to consider further in the alpha phase. And another thing that we found is obviously this is a new technology and there's a lot of gaps in the standards, both electrical and structural, relating to superconducting cables, superconducting wires, sorry, and how they would be integrated into the network, how they would be tested, all these different things. So that's another key area that we'll have to look at in the later stages of the project. Next slide, please. Onto the costs and benefits. So we did a generic cost benefit analysis of a SCOHL system against a 400 conventional overhead line, which would achieve the same power flow but in a smaller footprint. What you can see from that graph is the SCOHL cost is higher, but achieving cost parity is thought to be possible because, first of all, there'll be cost reductions as the technology develops. We're obviously looking at a technology that's being moved forward very quickly through its development phase at the moment, and as we develop that, costs will fall. And also, lower voltage deployment will lead to lower substation costs, smaller towers, and the potential to reuse infrastructure like towers rather than building new ones. These haven't been looked at because they're very very case and location specific. So that's something that we will do in the alpha phase. We'll look at a specific case and do a more detailed cost benefit analysis to show the cost savings or cost parity that can be achieved with superconductors. Next slide, please. Okay, and another thing that we did in discovery was we engaged with a number of other stakeholders, which we found very valuable in scoping out the problem and finding some items of specific interest and getting some technical details that we in the project team didn't have enough expert knowledge on. So we engaged with a couple of grid customer organisations, and we're looking to include a bit more perspective from them in the alpha phase. We spoke to Scottish Power Renewables, who are a generator, significant renewable generator, and Microsoft, who are a large consumer of power and particularly interested in how they could get fast connections for data centers, which obviously are big power consumers in a small space. And we had some discussions with additional experts for some items that we needed to know a bit more detail about. So we spoke to Balfour Beatty, who are an installer of HV lines. So we wanted to understand the differences between how you would install a superconducting conductor versus a conventional conductor. And we got some very good insights from them. And also Allied Insulators, who design insulators, as is in the name. So we needed to get some information on the structural and electrical properties of insulators. So we've spoken to them about that. Next slide, please. Yeah, so this one is sort of just outlining the roadmap that we see for the progress to business as usual for this technology. We've obviously already done the discovery phase. In the alpha phase, we see, as I've described, developing a use case, doing a detailed cost and benefit analysis on that, and some detailed modelling of the electrical and structural parameters that we talked about. And also on the technology side, partners moving towards progressing the development of the technology at a higher voltage. And then we have plans to go through the beta and the beta phase and future phases, which we can maybe talk about in the questions, because I've gone over my time. So next slide, please. Yeah, and the alpha phase, really, we just need to fully understand the significant issues and challenges, technical, regulatory and commercial, how those interact. We're proposing 4 work packages, 2 to deal with technical and standard issues, 1 electrical, 1 structural, and 2 to deal with the wider commercial issues and to draw together the strands from the first 2. So that's our plan for alpha. And next slide, please. I think that's me finished. Yeah, thank you. Hand over back to you, Beth, for the questions.
Brilliant. Thank you, Alison. Great presentation. We do have a couple of questions coming in, or maybe more, in the Q&A, which is good. So I'm going to start with those. So first question is from an anonymous attendee. How much deployment of this tech is estimated to be deployed in the medium term? And is there enough of a market size to drive a steep learning curve?
Okay, that's a good question. I can maybe hand over to Jessica for that one to talk about the development that they've been doing, and then we can maybe pick up with Sean about the GB perspective, perhaps?
Yes, that sounds good. Thank you. Ironically, the other industries are actually helping us bring down the cost. So the largest component cost of our overhead lines are the HTS tape, and the fusion industry is having significant investment to try to develop their technology. That has in turn prompted increased manufacturing. Most of the HTS so far has been research driven or demonstration project driven. So we see a steep decline in that. And then in addition, this problem that we're addressing is really a global problem. And so the ability to drive volumes through not just the UK, but other locations around the world, I think can help us give confidence that the cost will come down. Thank you.
Okay, thank you very much.
Sean, I don't know if you want to maybe make a comment just on the potential for this in GB. And we've talked a bit about it in the slides, but whether there's anything you'd like to add to that.
Yeah, thanks, Alison. No, I mean, at the minute, you know, in order to deploy it onto the GB transmission system, it would have to be a viable option at those transmission levels, which is what this project is all about. But thinking about how much capacity we need to increase on the network to facilitate net zero, there'll be plenty of opportunity 2030 and beyond. So it's really important, vital that we explore all those options that allow us to expand the network during the 2030s and beyond.
Thanks, Sean. Okay, next question is more of a comment around when's the best point to upgrade the HV lines? So Rob Walden says, presumably because of the cost of replacement, it only makes sense to upgrade HV lines when they're at the end of their life, unless, of course, there's a reason to increase capacity. So it's more of a sort of open-ended comment. I don't know if you have any insights on that.
Yeah, I mean, I could suppose approach it from the aspect of we would upgrade or replace conductors under two scenarios. One is when there's a load-related driver that requires us to upgrade the line to increase capacity of an existing line. And the other one is the end of life of the existing asset. Under those circumstances, we ordinarily would only upgrade. We wouldn't upgrade, we would replace like for like, unless there is a requirement and a business case that means we'd need to upgrade it for future capacity. But that would only be in agreement with Ofgem and consumers.
Great, thank you, Sean. There's another question from an anonymous attendee. Is the challenge that the suppliers are not able to find alternate gases or mixtures that meet the safety insulation character? Oh no, sorry, that was from the previous project. Excuse me.
Hi Beth, yeah, I think that was a lagging question from the last session.
Oh, I've done a lot of these show and tells. We get a bit of overlap. Apologies on that one. Have you assessed if there are any issues relating to the performance of this technology under fault conditions?
I'm going to hand over to Wager for that one. If Wager's available, sorry.
Oh yes, so I think that performances will be in the alpha phase. We identified it's important to study the protection schemes for both steady state and the transient state. So because of the short duration of discovery phase, we managed to get steady state characteristic, but for the transient characteristic, the alpha phase will give us enough time for us to do a proper study with within the chosen network.
Thank you.
I don't know, Alison, do you have anything to add on?
Nope. No, that was good.
Sorry, Jessica, do you have anything to add on?
No, that's good. Thank you, Wager.
Brilliant. That brings us exactly to time. So thank you so much to the Superconductor Overhead Lines team and everyone who contributed to the show and tell. Really appreciate it. I would like to invite our final project, D-Suite, which is led by Scottish Power Energy Networks, to present their show and tell presentation. Do we have
Thank you very much. Yes, here.
Fantastic. Over to you, Andrew. Thank you.
Thank you very much. Yes, I'll just dive straight into the content. So can I have next slide, please? Thank you. So my name is Andrew Moon. I'm a lead engineer at SP Energy Networks, and I work in the SP ManWeb region. And we've run historically some power electronic projects in Spain. One of them being Angle DC, which is a medium voltage strategic project, and the other one being LV Engine, which is a smart distribution transformer project at the LV level, which gives us some background and expertise in this technology. And we also have a project partner on board, UKPN, who have led soft open point projects as part of the network innovation competitions and LCNF over the past 10 years, so they have a good background too. So going into the slide, what we're going to present today, we'll just show you the introduction to the project, why we're doing D-Suite, what are the drivers for it, and then we'll just break the presentation down into the various work packages. So this was customer requirements, what do the customers want out of it, and what functions does the technology give us. And then as part of the theme for the discovery phase round 2, we did a literature review and went out to suppliers and supplier base in Europe and America. So that'll be our partner presenting on that from Newcastle University. And then we also developed some detailed design specifications and ratings for each technology that's going to be used on the LV network. So our partner at Integrated Power Tech, which is a spin-off company of Cardiff University, will take us through that detail. And then work package 4 is roadmap to commercialization, which is very similar to the structure of Alpha that we've developed as part of the project. So I'll introduce you to that and run you through the detail, and then we'll go into Q&A. So next slide, please. And again. Thank you. Okay, so drivers really mainly are about the government trying to roll out electrified heaters as quickly as possible, and also electrified transport. And the two drivers you've seen recently in announcements are 600,000 heat pumps, towards the end of this decade, and the ban of electric vehicles towards the end of the decade too. And then, as people mentioned on their presentations, the net zero target. So in the UK, we typically have single phase connections to properties, and these are thought to be reasonably well distributed across the phases, but there is masking of exactly which customers connect to what phase, and whether there's any phase imbalance, which will drive issues later on. And these issues will become apparent when we increase penetration levels of heat pumps, EV chargers. At domestic level would be 3.5 to 7 kilowatts, and things like photovoltaic panels. I doubt we'll see wind, but it's mainly photovoltaics. So when we do increase penetration levels of things like PV, we see voltage rise issues and difficulty maintaining within statutory limits towards the end of the feeders, especially on radial circuits. And we also see on interconnected networks, we can see load sharing unevenly between secondary substations, which can lead to low impedance paths getting on the load, and then those transformers being near their limits, while other transformers aren't, they're underutilized. And then as we put heat pumps and big loads onto the network that are continually operating, they're not variable, they're operating throughout the day, we could see large phase imbalances, which will increase the utilization of one phase, where it could leave the other phases, the LV phases, fairly unutilized. So we've seen two of these technologies rolled out previously on trial innovation projects, which brought the TRL up to its present levels. And those were the DST, which is a smart distribution transformer, and also a DSOP, which is a distribution soft open point. And they can do similar things to a certain extent, but the smart distribution transformer is mainly enhancing the functionality of a normal transformer and sticking the functionality of power electronic devices at either end on the LV and the HV side. Whereas a soft open point does the similar thing without the transformer present, but it does that at the end of the feeders and in between two different networks, and transfers power across two networks where it couldn't do normally. So this can improve load sharing across transformers, as I mentioned before. And then the top one here has never been done in the UK level, which is an LV StatCom. And LV StatComs are mainly used to control power factor and reactive power. And they can do that very fast, and they can provide rapid response. And they can also improve phase imbalance. So they're connected to three phases, and they can power share between the phases. And if they're placed optimally, they can improve the phase imbalance issue where they're placed. So these are very promising technologies. And we'll just roll out into what we've done for work package 1. Next slide, please. And we go. Okay, so what we did here was we looked at our network as it stands today, because we developed a modeling tool called Navi, which is kind of inspired by ENW's project, which was LV Solutions, and that used changed the GIS model into a connectivity model, which you could derive network models from for power flow studies. So we've taken that idea ourselves and made a tool out of it for our LV design engineers and LV planning engineers. And that means that they can interface with a map anywhere across our license area, and then click anywhere on the network, and it will connect all parts of that circuit up to its nearest substation. And then you can download that program and all of the asset data within that program. And then you can superimpose different LCTs on top of it. And it's mainly a steady state model at the moment, which is adding LCT levels based on where you are in time, based on our distribution for generic energy scenarios. So the bottom picture here, you can see that the heat pump level is starting off slow, but it's accelerating towards 2040. And then the top part of the graph is showing the EV penetration levels increasing dramatically. And on the right, then we took those snapshots in Navi and showed that our networks are getting more heavily utilized on a thermal basis because it's carrying more current to customers. And at some point during that period, there will have to be an intervention on some networks that we analysed. They're quite a high proportion of them that we picked. It's only a small sample, but we think that's indicative. So it's just showing, this work package is showing that there is a use case for D-Suite technologies, and we need to be thinking about how to do that as fast as possible. So anyway, I'll roll on to work package 2 then. If you just go on to the next slide, please. And again, and this was done by Newcastle University, so I shall hand over to the lead, which is Matt Deakin, Dr. Matt Deakin.
Okay, thank you. Yeah, so in work package 2, we were looking at a literature review and engagement with potential suppliers for these technologies. So power electronics are sort of everywhere now in the power system at all levels. But this is sort of, as Andrew mentioned, this sort of new LD suite is a sort of new potential application for power electronics. And there's these 3 aspects that the project is interested in that make it a bit unique as compared to sort of power electronic projects more generally. So we're looking at low voltage distribution. We're interested in grid connected systems rather than microgrids. You find lots of research about microgrids and power electronics. And also we're just focusing on conventional AC rather than sort of mixed AC or DC distribution. And so because there's been so much innovation in this space, we wanted to do a sort of deep dive in this discovery phase, and there's sort of 3 aspects of that. So firstly, we had a holistic review of both historic and ongoing power electronics projects so that we could look at the different types of innovations that people are doing. So for example, you can see on this figure here, there were 6 innovations that we identified from those projects, of which 3 were included within the D-Suite sort of innovation proposal going forward. We then wanted to look at the challenges that these devices have, sort of the challenges to widespread rollout, and then also talk to potential suppliers for that alpha and beta phase going forward. Next slide, please. So the project review that we undertook, so we had a sort of 3-pronged approach. So we looked at the Smarter Networks portal, which obviously has huge amounts of information on there for UK-based projects. For European projects, we used the Cordis database, and for the US, we looked at the ARPA-E project database. We surveyed 54 projects, and across those projects, we identified that there are 9 challenges that are sort of common to all of those, in terms of the barriers that power electronics face for providing capacity within the D-Suite. So cost, reliability, these are all sort of things that might be familiar to colleagues. And the innovation types, we found that there were 6 sort of technology classes that were relevant. And having identified those, we spent quite a bit of time reviewing literature, seeing how those different innovation classes can impact on those challenges. So this figure at the bottom that you see here, this is, we've evaluated how effective different types of innovation are against those challenges. And you can see it's quite patchy actually. So you really, if you want to sort of move forward across the board, you really need to be starting to combine those technology classes within a project. So we think that that approach that D-Suite is taking is the most effective one. So as well as that, so in terms of the sort of work package output, so there's that matrix that I've just described. The project database is also given in the report, where we outline the sort of different challenges and technologies that each are looking at. And then, as I mentioned, we identified 18 suppliers that could each develop at least one of the D-Suite technologies that Andrew outlined earlier. Next slide, please. Okay. I'll pass back over to Andrew.
Yeah, thanks, Matt. That's good. Yeah, so Wenlong, would you like to present your hard work on the discovery stage for package 3?
Yeah, thank you, Andrew. I'll take over from. Yeah, so following on the literature review, so what we are doing, what we did in the work package 3 is to specify the design parameters for the hardware and the control algorithm. for these DSU technologies. So as Andrew mentioned earlier, so we're focusing on 4 types of DSU devices, which are the STACOM, the SOP, the smart transformer, and the HF, which is the harmonic filter. So we have done 3 things. So one is to develop the hardware solution, which means mainly about the topology. So we develop different type of topologies for these different devices. But what we also did is to develop a modular structure for this device, which means that they'll share the same architecture for the basic unit. Then if you want to construct a different type of these devices, then you just need to pick up more modules and then put them together, connect them together, and then you have different type of DSU devices. So that is mainly for the consideration of the cost. The other thing we have done is to do the hardware design on that module, to design the parameters, for example, what kind of switches we're using, capacitors, inductors, how to optimize them, and how to protect them under the grid fault, and also consider the internal fault or voltage over current. So the last thing, but not least, we have done is once we got that hardware, then we developed some control method. Again, it's modular, have different layers from the bottommost switch layer control and up to the system layer control and interaction with the system. So can you go next slide, please? Right, so in terms of the a bit more details, what I mentioned the previous slides. So for the topology design, as I mentioned, we identify a 3-phase 4-wire structure as a most basic module for the DSU devices. And then, for example, for the DSOP, then essentially we just need 2 of them connected back to back. Then we have the DSOP, the software component. And for the smart transformer, again, we need them back to back, but one of the converters can be connected in series with the transformer, with the help of auxiliary transformer, which is partially RT1. And last example I gave in the middle is the can be a D harmonic filter. So you just need one the more module, which is a 3-phase 4-wire converter. Then you can inject or absorb different type of harmonic into the grid. It can be used as DSTACOM as well. Basically, they share the same hardware. So the difference is about the control, comes from the control. And the most right side, you see what I mentioned, different layers from the hardware control, switching, converter applications up to the system level control. So we designed the general structure of this control strategy and topology in the discovery phase. So going to the next phase, we're going to investigate more details. Like, for example, we have the module. So how can we optimize that module in terms of the cost efficiency, the power density, and we investigated the size, the investigate control as well. But we need to do more investigation on the protection side, especially under the grid fault. Can you go to the next slide?
Sorry, are you able to start to conclude your presentation, please, as we are coming to the end of the session?
Yeah, I think this is a summary for the work package 3. So I think I mentioned the majority of the point, but one thing I want to highlight is, so the DSU devices, we got 4, but there might be more depending on the functionality needed. But what I want to highlight is they share the same modular structure. So basically you connect them in series, in parallel, so we can provide different functionalities as what is needed from the grid side. Andrew, hand over back to you.
As well, I can zoom in here, or I can just do very quickly 1 minute on the route to market and close. Up to you.
Sure, that sounds great. Just a quick summary would be fab.
Yeah. Next slide, please. Yep. So route to market then. we structured this according to the alpha if we were successful. So the idea is work package 1 is to understand the value streams better by doing detailed network modeling on very accurate networks in minute by minute or half hourly by half hourly over the year, and then test those control philosophies and release the technical benefits for the business case. The second part of that is to nail down the hardware in terms of modularity, and then create a detailed technical specification for tender. And then this would then go into the business case standards review output for the project and work package 3. And then work package 4 then it takes work package 2 outputs to develop the PQQ pack, which will be like a very early draft of technical specification. Send that out to the market to the suppliers we've identified in this discovery stage, get costs and comments back to see what's missing from our tender pack, and then update that tender pack for final version ready for a beta stage if we're successful. And then while we're doing all that work from work package 1 to work package 4, we'll also be going out to various sites we've identified in this discovery phase to see if they're eligible for D-Suite installation, and any of those that weren't eligible, we have contingency to select new ones and then appraise them and have them ready for selected sites by the end of the alpha stage, ready for beta. Okay, thank you very much for listening. I'll hand over to Q&A. Thank you.
Thank you so much, D-Suite. I really appreciate that presentation. We have time for one quick question from Rob Walden, which is about the communications between the devices and the cloud-hosted services for correct operation. He says, what consideration has been given to the failure modes and reversionary modes of the operation when communication is interrupted?
That would have to be done in the alpha stage. So we have experience on LV engine and angle DC for maloperation of the control system, which we're bringing into this project. But you need to do the detailed control studies first to understand where your monitoring points are going to be, what visibility you have of the network, and how that affects the behavior of your equipment, and is that operating within a safe operational envelope all the time. And if you lose comms or connection to your central system, what will your actively controlled device do in that scenario? And you have to have default settings which these things reduce back to. And if they reduce back to a certain extent, will that affect your benefits, the benefits that are released to allow more customers to connect to PV, for example? Could we run, say, a DStatCom in a reduced operating mode and still have the required penetration levels of PV that have been released, or do we have to think of something else? So these are questions that we'll have to answer in the alpha stage, because it's very detailed modeling that needs to be done.
Brilliant. Thank you so much. There is one more question in the chat. I'd like to invite you or the rest of the team to type an answer in the Q&A box, please, as we're going to have to wrap up. Thank you, D-Suite.
No problem. Thank you.
Big thanks to all the projects who presented today. Really appreciate you sharing all the things that you've learned through the SIF discovery phase in round 2. I would just like to highlight we have some more show and tells coming up. Tomorrow we have one in the morning on flexible heat networks, and in the afternoon we have unlocking flexibility for heat decarbonisation. We have one on Friday, and all the way through we have one a day through to Wednesday the 21st. So please tune in, drop in where you can, really appreciate it. And yeah, hope to see you soon. Thanks everyone for joining. We'll close it there.
Thank you.
Thanks all.